Today we're going to work a couple more examples of 3D rigid body equilibrium. So this next example that I have is a kind of bent pipe or bar or something, and it's being supported by, it says it's a roller support at B, so it's sitting on the ground basically. The ground's going to provide an upward normal force. And the other place that this bent-shaped bar is supported is it's got a collar on this bar over here that's fixed to the wall in some way. We're not interested in analyzing where it's fixed to the wall. We're interested in just analyzing it from the collar on out, because the problem asks us to find the support reactions at collar A as well as at the roller support B. So I want to start with a free body diagram. No surprise there. And we'll just kind of make a stick figure diagram, kind of like so. At B, I have removed a roller support. So a roller support provides a normal force. You can call it either the normal force at B, or if you prefer, you can call it BZ, as it points in the upward Z direction because it's sitting on the ground. And then at A, we had a smooth collar. So the idea over here at A is because that collar is smooth, it is free to slide along this pipe or bar over here. So it's free to slide in the X direction. That means we will have no reaction force in the X direction. It's also free to rotate about that same axis, the X axis. So what that means is there will be no reaction moment about the X axis at point A. But that collar is going to prevent translation up and down, translation in the Y direction, as well as prevent it from spinning about the Y-axis and spinning or rotating about the Z-axis. So at A, we'll have the other four reactions. So let's draw them on. We'll have an unknown reaction AY and AZ, just guess whatever direction you'd like. And then we'll have reaction moments as well about those same two axes. So a moment at point A about the Z-axis, and a moment at point A about the Y-axis. And then we also have two applied loads, a downward 800 Newton force and a downward 600 Newton force. That should be everything on the free body diagram. They didn't tell me anything about including the weight of the pipe. So we've just got the two applied loads, the normal force at B, and then the four reactions at A. So if we want to count up our unknowns, I'm counting 5. NB, AY, AZ, MAY, and MAZ. So I've got 5 total unknowns to solve for, so I will need 5 equations. Our next step in this problem is going to be just writing out equilibrium equations. And the reason we can jump straight to that is all of our forces are just in the X, Y, or Z direction, so I don't need to get any vector components. So if we start with forces in the X equals 0, I don't see any forces in the X direction. There are none. So I just get 0 equals 0, not a helpful equation, and that's the reason we're only going to have 5 unknowns to solve for. Let's try the Y direction. The Y direction is this way, assign a positive sense, and in that direction I've got AY and nothing else. All the rest of the forces are in the Z direction. So AY is just equal to 0. One unknown down. Let's sum forces in the Z. Our other force equation will give us upward, I've got AZ and NB that are both unknown. And downward, I've got 800 newtons and 600 newtons. And that has to sum to 0. Can't solve for either of those unknowns yet, but I will use this equation in a couple of minutes. If we run out of force equations, we are going to have to do moment equations next. So let's try summing moments about an x-axis. Has to equal 0. We'll call positive, with our thumb pointing toward the positive x direction, a positive rotation sense. And I need to pick which x-axis to sum moments about. You want to pick an x-axis with a lot of unknowns. So I'm going to go with this x-axis. Although if you feel like it, you could do this x-axis over here. Either way, you're going to knock out an unknown, because over here, NB would have no distance. Over here, AZ would have no distance. I picked to do some moments about point A, just because it's the most complicated place on the whole diagram. So summing moments about the x-axis through point A, the forces at A have 0 distance away, so they cause no moment. This moment is about a totally different axis, so it does not contribute to the moments about the x-axis. You would include this only when you sum moments about the z-axis, and you'd include MAY only when you sum moments about the y-axis. So none of this, all of this will not contribute at all. So moving along, My x-axis is here. The 800 newtons looks like it will cause a moment. The perpendicular distance would be this length right here. Since we're summing moments about an x-axis, the force is in the z direction. We are looking for a y distance, and that distance along the y-axis is 0.8 meters. So in my equation, I'll have 800 newtons times 0.8 meters. And if we want to know the sign of that, if I start over here at the x-axis, move to the right, and then go down, the rotation is going to be this way about the x-axis, and if I curl my fingers that way, my right thumb points in the negative x direction. So this one will be a negative moment. Moving along to the 600 Newton force, my x-axis is back here. The 600 newtons is a long distance away, so there will be a moment, and there's my perpendicular distance. So from the axis to the force, perpendicular distance is 0.8 plus another 0.8. So I will have 600 newtons, and my distance is 0.8 plus 0.8, or 1.6 meters. And that one looks like it will also be negative. We start at the axis, go out here, and the force points downward, so we're going to be rotating that way. Thumb would point in the negative x direction, so also negative. And then finally, NB will cause a moment. It is also 0.8 plus 0.8, or 1.6 meters away. So we'll have NB times, I'll just write it 1.6 meters away, equals 0. And NB, I think that's going to cause a positive moment. Start at the x-axis, come out this way, and then go upward. That is going to cause a rotation that would have my right thumb pointing in the positive x direction. So we've got plus. We can solve this. If we solve it, we get that NB is equal to 1,000 newtons. And the fact that it is positive means that I did draw it in the right direction on my diagram. If we substitute that back into our z force equation right here, we can solve for AZ, and that comes out to be positive 400 newtons. So it was also drawn correctly. These both act upward in the positive z direction. Next, we can sum moments about a y-axis and a z-axis. I did the x-axis through point A. Let's try summing moments about the y-axis. Let's see if A makes the most sense for the y-axis as well. I think it probably does. This actual y-axis on our part that goes through point A, that means that both the 800 Newton force and all the forces at A will cause no moment. We'll have MAY that we need to include, as well as any moment caused by the 600 Newton force and the normal force at B. So we're also going to sum moments about the y-axis through point A, which is the actual y-axis on the picture. We've got our unknown reaction moment, the moment at y. It's the couple moment that's caused by that collar to prevent this from rotating. And I drew that, assumed it was positive. Next, we need this downward 600 Newton force. We need to know the perpendicular distance from the y-axis. That's going to be this length right here, the 0.4 meter distance. So let's add in here 600 newtons times 0.4 meters, and then I believe, let's see if that's going to be positive or negative. Our axis is here, we go that way and then down, so we're going to be rotating this way. If you curl your fingers that way around the axis, your right thumb ends up pointed in the negative y direction. So this one's going to be a negative moment about the y-axis. And then finally, NB, we need a perpendicular distance. So from the y-axis out to NB, the distance will be 0.4 plus 0.4. So we've got NB, which I know is 1,000 newtons, times 0.4 meters plus 0.4 meters. It's all going to equal 0, and then is NB going to cause a positive or negative moment? The axis is here, position vector goes out that way, and then the force vector goes up. So we're rotating this way, which if you curl your fingers that way around the axis, it's going to be a positive moment because your thumb is pointed toward the positive direction. Substitute in the 1,000 newtons for NB, and what we get is that the reaction moment, MAY, is equal to minus 560 Newton meters. That means MAY is 560 Newton meters about the negative y-axis. So you'd have to put your right thumb pointing toward the negative y direction and that is the direction that it would actually rotate. So point your thumb toward the arrow, fingers curl around. Almost done, we just need to find MAZ next. So if we sum moments about a z-axis, let's just stick with point A. There would be my positive sign convention. I'll have MAZ in my equation, my unknown reaction couple. And now since we're summing moments about the z-axis through point A, none of the forces at point A cause a moment. What about the 800 newtons, 600 newton, and NB? They definitely are not located at that z-axis, but did you notice they are all pointed in the z direction? Thing to keep in the back of your mind is always, in order for a force to cause a moment about an axis, it has to be perpendicular to the axis. So if the force is parallel to the axis, it does not tend to cause any rotation about that axis. So none of these z forces will cause a moment about the z-axis. So MAZ is the only moment on this entire diagram, so it has to equal 0. And we're done with that problem. Next thing we did in class was to do a couple of concept questions in Top Hat. So the main concept question here that I wanted to drill home was, again, that idea of, will a force cause a moment about an axis? So first question to ask is, what will be the moment, or will this 300 Newton force cause a moment about the x-axis? 300 Newton force, will it cause a moment about the x-axis? And the answer to that question is no, because it is parallel to the axis. So a force cannot cause a moment about an axis if it's parallel to the axis. How about a moment about the z-axis? So to find the moment about the z-axis caused by that force, which length will you multiply it by? So we're looking at the 300 Newton force. There's the z-axis. If I want to find the moment it causes, I need a perpendicular distance between the z-axis and my force, and that's going to be that green 2 meters. That's the distance you need to multiply the 300 newtons for. Will it be positive or negative? Well, since you come out this way and go that direction, so your position vector from the axis to the force is that way, force vector is in that direction, it's going to cause rotation that way, it's going to be a positive moment about the z-axis. And then finally, third question is, still focusing on this single 300 Newton force, and I want to find the moment it causes about the y-axis. There will be no moment about the y-axis because it's directed straight through the y-axis, so there's no distance, right? If the force goes right through the axis, or is even if we're over here and just pointed at the axis, it won't cause the part to rotate about that axis because it doesn't have a distance away. To cause it to rotate, it would need to be either up here above or down here below, but it's not. It's right over there, pointed straight at the axis, no distance, no moment. We have a couple of additional problems that I didn't get to in class, but they're kind of useful to think about. So we're just talking about if I were drawing the free body diagram of this pipe. It's fixed there at point A, so what would you draw on the free body diagram at point A? At point A, it's fixed in all directions, so you're going to need to include an AX, AY, AZ, a moment at A about the x-axis, a moment at A about the y-axis, and a moment at A about the z-axis. Because it is a totally fixed support, can't move in any direction, so all of the reactions need to go on it at A. How about this next one? What goes on the free body diagram at A? It's a ball and socket. Ball and socket allows rotation, but it does prevent translation in any direction, so we're going to need AX, AY, and AZ, which is typical of a ball and socket. How about this one? What goes on the free body diagram at the hinge at A? We do need to know whether or not it can support axial thrust. Is it basically like a journal bearing or a thrust bearing? So let's assume it's a thrust bearing or a thrust hinge. In that case, because we've got a pair of hinges, we're not going to put any reaction moments on either of those hinges. But if it supports thrust, then you're going to have an AX, AY, and AZ. If it's a journal, we don't really call it a journal hinge or a thrust hinge, but if it were a journal bearing, then it would be only AX and AY, because the axis of rotation is a z-axis, so that's the direction where you would include the reaction if it's a thrust bearing, but do not include it if it's a journal bearing.